Okay, take a moment to jot down this next optimization problem. We're dealing with a 4,000 cubic centimeter container. It must have a square base, vertical sides, and it has an open top. We want to find the most economical shape which minimizes the amount of material needed. So it's not explicit with telling us exactly what it is we're trying to minimize. If we're talking about the amount of material needed, this is referring to the surface area, which we can abbreviate with SA. So draw yourself a little sketch here. It needs to have a square base, so let's call those sides X, and then we have some height. Alright, so we're told that we have a 4,000 cubic centimeter container. From that, you have to gather that that means it's the volume. So the volume is 4,000. Now, we also know that the volume of this shape would be x times h, which would be x squared times h. So that means that 4,000 is equal to x squared times h. Okay? Now, we're just going to keep that in mind for now. We need an equation for the surface area. We're not looking to minimize the volume, we're looking to minimize the surface area. So that means we need a surface area equation. So let's think about how we can write an equation for this. It has a bottom. The area of the bottom would be x squared plus, remember there's an open top, so we have 4 remaining sides, and each side has dimension x by h, right? So from there, remember we want to rewrite this all in terms of one variable. So up above, we set up here that 4,000 is equal to x squared times h. Well, we're going to use this equation to help us solve for one variable. H is same as 4,000 over x squared, right? So I'm going to replace my h with 4,000 over x squared. Okay. So our surface area equation here, let's clean this up as much as possible. We would have x squared plus, now that you can do the 4 times the 4,000, so you have 16,000. Right, and this would be all over x, because that x and that x squared would simplify to just give you one x in the bottom. Keep in mind that we're going to have to eventually find a derivative. So let's rewrite this so we can avoid using the quotient rule. Let's rewrite this as x squared plus 16,000 times x to the negative 1. Okay, so from there, let's find our derivative of the surface area. We're going to have to set it equal to 0 and solve, just like before. Okay, so let me take you through what we just did here. So we found the derivative using our power rule. I rewrote this x to the negative 2 as a positive in the bottom there. From there, we're going to set it equal to 0, right? And to solve this, what you can do is add over that 16,000 over x squared term, and then we can put this over 1. We can cross multiply. We get 2x cubed equals 16,000. We can divide that 2 over, and then take the cube root to get x equals 20. And then we can go back to our h equation from up above, drop in a 20 for x, and get our h value as well. So the most economical shape would have an x value of 20 and an h value of 10. Now, don't forget, we have to confirm that x equals 20 really is a min. So let's use the second derivative to do that. Take a moment, find your second derivative, plug 20 into it, and go through that same process to prove that it really is a min. So here's what that would look like. Our second derivative, so I'm looking at the derivative of this equation right here. So that would be 2 plus 32,000 x to the negative 3. I then rewrote that x to the negative 3, and the bottom here is x to the positive 3. So we're going to plug 20 into this. And again, we don't care about the actual value. If we plug 20 into it, we can see that it's going to be something positive. So the second derivative is greater than 0. Therefore, the original surface area equation must be concave up. And if it's concave up, it guarantees that that value, x equals 20, must be a min. So again, we're talking about it being concave up, so therefore it must be a min. All right, in our last example here, we are looking to manufacture some cans. All right, they're cylinders, and we want the cans to contain 100 cubic inches of beverage. We want to know what height must each can be to minimize the amount of aluminum to make the cans. So we're looking to minimize the surface area. Okay, so eventually we'll need a surface area equation. Now, all we know is the volume, right? That anytime you see cubic inches or cubic, whatever the unit is, we're referring to volume. So we know that the volume of a cylinder is pi r squared h. Think of it as the area of a circle. The bottom area of a circle is pi r squared times the height of that can. So that's the volume. All right. So we know that 100 is equal to pi r squared h. All right, so let's leave that equation for now. Let's look at writing a surface area equation. So the surface area of a can here, it has a top and a bottom. Top and the bottom are both circles. So area of a circle is pi r squared. We need two of them. So we have 2 pi r squared. Plus, now we need the curved portion going around. Well, if you were to open up that curved portion going around, it's really a rectangle. All right, and that rectangle would have dimensions of 2 pi r and h. All right, so again, if you were to open this up, the rectangle, one length is h, the other length is really the circumference going around the circular part. 2 pi r is the circumference piece. Okay, so that is your general surface area equation for a cylinder. So once again, remember, we need to get this in terms of one variable. We see a couple r's in there and there's an h. So let's make the decision to do this all in terms of r. So let's rewrite h in terms of r. So let's go back to our volume information. To get h, we would have 100 divided by pi r squared. So let's substitute that in here. So our surface area equation would be 2 pi r squared plus 2 pi r times h, which is really 100 over pi r squared. So take a moment and clean that up. So after cleaning this up, we have at the bottom here 2 pi r squared plus 200. Notice how the pi's would cancel each other. You have an r over r squared, which becomes r to the negative 1. So now we've simplified it. Now we're ready for our derivative. So go ahead, find your derivative, and set it equal to 0, and solve for r. All right, so let's check what you have. So right here we have our derivative. And keep in mind 2 pi is just a number, so when you multiply 2 down to it, you get 4 pi, and then r minus 200 r to the negative 2. I then rewrote it with a positive power, set it equal to 0. Take that 200 over r squared and add it over, so you can then cross multiply. Over here we get 4 pi r cubed equals 200. We're solving for r, don't forget, so let's divide over that 4 pi. So then we can clean it up a little bit, turn it into 50 over pi. So to get our r, we need to take the cube root of 50 over pi, and that is going to give us an r value of 2.515. Again, we're using a calculator here. So let's now confirm that this really is a min value. So once again, go through the process of using the second derivative. So we find our second derivative. So I found the derivative of this equation. So 4 pi is a number in front of r, so you just end up with 4 pi plus 400, and then it's r to the negative 3. I wrote it down here as all over r to the positive 3. Remember, we're plugging in this value of interest of 2.515. If you plug it into your second derivative here, all we care about is the fact that it's going to be, in this case, positive, right? So that means since the second derivative is positive, therefore it's concave up, and this r value must be a min. Now, it's easy to stop there and say, okay, I'm all done. Well, go back and reread it. We are looking to find the height. So that means we need to go back and plug in and find our height. So do that. All right, so take 100, all divided by pi times that value squared. All right, and when you're doing this, make sure you put all of this in parentheses in your calculator. Okay, you want to make sure you're dividing by that entire amount. So it's important to put parentheses around this entire quantity. And when you do that, you're going to get a height value of 5.03. It actually has a 2 on the end here. All right, remember AP always wants 3 digits after the decimal. And let's not forget our unit here. We're talking about inches. So this is our final answer to the question.